Hi everybody, in this video we're going to talk about exponential functions and I'm going to introduce them in the context of comparing them to linear functions. So in a linear function, the pattern is a consistent either addition or subtraction pattern. So in this penny jar example where you start with 2 pennies and on each day you add 3, the function that represents this situation would be a linear function because you're consistently adding 3. So like you add 3 to 2 to get the 5, then you add 3 to the 5 to get the 8, then you add 3 to the 8 to get the 11, add 3 to the 11 to get the 14, and so on and so forth. And the function rule that we found for this example is that the number of pennies, which is written as the output of the function when you input an x, equals 3 times the input, which is the day number, plus 2. And the reason why this function rule describes this pattern is because if you were looking at day number 6, well, the way that we get this number 20 is we take 2 and we add 3, 1, 2, 3, 4, 5, 6 times. And so that's where this 3 times 6 would come in because for day number 6, x would be 6. And then the 2 comes from the fact that that's our starting amount that we're adding the 3 to consistently. So that's an example of a linear function. Now, an exponential function is different from a linear function in the sense that the pattern is not consistent addition or subtraction, but instead it's consistent multiplication. So let's say we started with 5 pennies and each day the number of pennies doubled. So in this case, you're not adding a consistent amount, you're doubling the number of pennies. So 5 times 2 gives you 10 pennies on the first day. Then when you double that number, that gives you 20 pennies on the second day. And then when you double that number, that gives you 40 pennies and 80 pennies and so on and so forth. And the pattern is that you're consistently multiplying by something. And so if we wanted to figure out how to get this 320 on the 6th day, well, the way that we got that 320 was we took 5 and multiplied by 2, 1, 2, 3, 4, 5, 6 times. And so what that means is that we're repeatedly multiplying by 2 6 times, which we can write as an exponent. Because if I do 2 times itself 6 times, a simpler way to write that is 2 to the 6th power. And the number that I'm multiplying by 2 6 times is my starting number 5. So I would write this as 5 times 2 to the 6th power. And technically you could put parentheses around this if you wanted to show that it's just 2 to the 6th power, that you're not doing like 5 times 2 and then raising it to the exponent. But you don't have to put those parentheses there because the order of operations says that you do exponents first and then multiply. So if we wanted to write a function rule for the x day or day x, where x could be any number, like even like the 100th day, the way that we would write that is we would say the function when you input an x, or in other words, the output of the function is going to equal our starting amount times 2 to the power of however many days you've doubled the pennies. So in this case, x represents the day number, and f of x, or the output of the function when you input an x, represents the number of pennies you have on that day. So that's what the equation would look like that describes this exponential situation. And if we look at the graphs of these 2 penny scenarios, notice that the linear function, where you're consistently adding 3, forms a straight line type pattern, versus the exponential graph creates this kind of curvy pattern that grows really, really quickly. So like if you look at the y-axis here, after just 6, or like on day 6, you're already like in between 3 and 400 pennies. Versus on the linear situation where you were consistently adding 3 pennies every time, on day 6, you're only at 20 pennies. So exponential functions will grow way, way faster than linear ones will. And that's just the nature of multiplication because multiplication will make the number grow bigger faster than addition will. And I also want to mention that you can have exponential functions that decrease. So, an example of this would be if David had $1,000 and he decided to spend half of his money every day. So, in this case, our input and output, if we make a table for this, on day 0, he has $1,000. And on day 1, if he spent half of it, then he would only have 500 left. Then if he spends half of that, on day 2, he's going to have $250. And on day 3, if he spends half of his $250, then he'll have 125, and so on and so forth. So in this case, the thing that or the pattern that's happening here is that you're dividing by 2, but it's easier if you think about it as multiplying by a half, because dividing by 2 is the same thing as multiplying by a half. And so since you're repeatedly multiplying by a half, the way that this function would look is you would say that the amount of money he has after X days would be his $1,000 he started with times 1/2 raised to the x power. Because if you repeatedly multiply $1,000 by a half for however many days he's been spending half of his money, then that would give you the amount of money he has on day X. And if you were to draw a graph of this, the general shape of the graph would be curved, just like our last exponential function, but it would be curving in a decreasing way. So it would look kind of like this. And technically, this graph would never reach 0 because if you have a certain amount of money and you continually half it, you're always going to have a teeny, teeny, teeny bit of money. Even if it's like a really, really small decimal, you'll always have some money, and then you can find half of that, and then you can find half of that, and so on. And reasonably, it wouldn't necessarily be realistic to have like teeny, teeny, tiny decimals that go to like the 100,000th place because money, in at least in our money system, only goes to the hundredths place. And so it wouldn't necessarily be reasonable after a certain point, but the function will technically never equal 0. So that's an example of an exponential equation where it will decrease because you're consistently dividing by something, which you can also think about as multiplying by a fraction. So the general form for an exponential function is going to look something like this, where A is the starting value and R is the multiplicative rate. So in the example of the doubling pennies, we had f of x, which you can also represent with a y, equals, I think we started with 5 pennies and then we doubled it every day. So we had 5 times 2 to the x. And then in the example of spending the money slowly, we had f of x equals 1,000 times 1/2 to the x power. And so in both cases, notice that the starting amount is the amount that doesn't get raised to the exponent. And then whatever your multiplicative or division pattern is, that's the number that gets raised to the exponent. So if you're doubling it every day, you would do 2 to the x. If you're halving it every day, then you do 1/2 to the x. So that's the basic idea of exponential functions. And again, you're probably not going to teach this to your students because I'm pretty sure exponential functions don't get introduced till 8th grade and maybe even after that. So you won't ever teach your students all of the technicalities that I've shown you in this video. But it is possible for you to still build their conceptual knowledge of exponential patterns by giving them patterns that increase multiplicatively. So again, you'll see some examples of that in the case studies. And if you have any questions, please let me know.